The function of a turbine is to convert energy contained in steam to mechanical energy that is used to turn a generator. A turbine is an enormous machine and may seem indestructible. But in fact, a turbine is easily the most delicate and precise piece of equipment in a power plant. To operate a turbine safely and efficiently, it's important to have a basic understanding of turbine construction and operation. This is a diagram of a simplified steam turbine. Turbines are composed of moving parts, stationary parts, and systems of pipes and valves. We'll start with the moving parts, the shaft and the wheels. The turbine shaft runs the entire length of the turbine. This end is connected to the generator. The turbine wheels are connected to the shaft. A turbine wheel consists of a round hub and rotating blades, or buckets as they're sometimes called. The shaft and the wheels are collectively called the rotor. The rotor is supported by bearings and is housed in a casing which is sometimes referred to as a cylinder. Mounted to the turbine casing are diaphragms. They are positioned in the casing between the wheels. The casing and diaphragms are stationary parts of the turbine. Diaphragms are similar to wheels in that they are round hubs and they have blades. The diaphragm blades are sometimes referred to as nozzles. The distinction between diaphragms and wheels is the way they function during turbine operation. Diaphragms are stationary and their blades are fixed in position. Their function is to direct the flow of steam leaving one set of rotating blades into the next set of rotating blades. Wheels, on the other hand, are moving parts. They are designed to turn as the steam flow passes through their rotating blades. The rotation of the wheels turns the shaft and the generator. Diaphragms are sealed where the shaft passes through them to minimize steam leaking through this opening and bypassing the diaphragms. Typically, the pairing of one diaphragm and one wheel is called a stage. A turbine may have up to 25 or more stages. Our example shows 8 stages, but only 7 interstage diaphragms. There's another diaphragm before the first row of rotating blades. This diaphragm is called either a nozzle block or a nozzle box. As with the interstage diaphragms, the nozzle block houses a series of stationary blades that are sometimes referred to as nozzles. The diaphragm nozzles direct the steam from the steam inlet to the rotating blades of the first wheel. The steam then proceeds through the remaining stages of the turbine until it is exhausted into the condenser. Now, before steam can enter the turbine through the steam inlet, it must pass through 2 types of valves: stop valves and control valves. Stop valves, which are also called throttle valves, remain fully open during turbine operation. The principal function of stop valves is to shut off the steam supply to the turbine during a shutdown or under emergency conditions. Control valves are used to regulate the amount of steam flowing to the turbine. For this reason, control valves are sometimes called governor valves. Under normal conditions, the control valves are partially open to regulate steam flow during operation. Steam flows from the stop valves to the control valves through pipes. Depending on the turbine design, steam may also flow through a steam chest. A steam chest allows the steam to spread out and slow down so that the flow will be less turbulent as it enters the control. Impulse blades work in a manner similar to the blades of a pinwheel. Air traveling in one direction strikes the pinwheel blades and pushes them out of the way, causing the wheel to turn. With turbine impulse blades, a similar thing happens. This simplified illustration shows the configuration of turbine impulse blading, with the rotating blades and the stationary blades or nozzles. As high-pressure steam is forced through the stationary blades of a diaphragm, it speeds up. The steam striking the rotating blades causes the wheel to turn. Since the wheel is attached to the shaft also rotates. This simplified illustration represents a nozzle that is part of a rocket engine. Hot gases from the combustion of fuel are exhausted through the nozzle as they leave the combustion chamber of the rocket. The nozzle causes the hot gases to accelerate to a high speed as they pass through the nozzle's narrow throat and then expand. The high speed creates a reaction force on the rocket engine that is in the direction opposite to the movement of the gases. This reaction force propels the rocket engine. In a turbine, the moving reaction blades act like the nozzle in a rocket engine. Steam leaves the blades at high speed and creates a reaction force on the blades, and that causes the wheels to turn the turbine shaft. So far, we've been talking about a simplified turbine. Most large turbines are divided into sections, and each section is connected to a common shaft. In this illustration, there are three separate turbine sections: a high pressure or HP section, an intermediate pressure or IP section, and a low pressure or LP section. At times, the different sections are referred to as separate turbines: the HP turbine, the IP turbine, and the LP turbine. But operationally, they all make up one turbine. In another turbine design, the sections are connected to different shafts. In this example, the HP and LP sections are on one shaft, and the IP section is on another shaft. This arrangement is called cross-compounding. While each section of a turbine works according to the same principles, they are not identical. By the time steam has traveled from the high-pressure section to the low-pressure section, its volume may have increased as much as 150 times. The size of the turbine is increased. Second, some of the steam is removed from the turbine by an extraction steam system. The extraction steam is sent to the feed water heaters, where it is used to heat feed water. The steam in the turbine gives up some of its heat as it passes from one stage to the next. For this reason, it's often necessary to return steam to the boiler for reheating before it passes through the entire turbine. This reheating most often occurs between the high-pressure section and the intermediate pressure section. Reheated steam is returned to the turbine through reheat stop valves and intercept valves. These valves, along with the stop valves and the control valves, also provide protection for the turbine. As you know, turbine speed is regulated by the control valves. If turbine speed increases during normal operation, how do you think the control valves will respond? If turbine speed increases, the turbine control valves will compensate by closing. To prevent overspeeding, the intercept valves close, cutting off steam from the reheater. If for some reason the speed continues to increase, the turbine trips. When the turbine trips, all four types of valves, the stop valves, the control valves, the reheat stop valves, and the intercept valves, quickly close, cutting off all steam to the unit. A trip protects the turbine from danger by immediately shutting off steam flow to it.